So, good morning everyone, and thank you for joining to my Java streams, evolution from Java 8 to today. I'm Mihaela, I'm a software architect at Systematic. This is a Danish company specialized in building software for what we call critical domains, such as building software for the military domain, which represents the business units for which I'm working. But we also have others like healthcare, digital, and libraries, and national security risk, and many others. And I guess something is wrong with my microphone, so give me one second. Yeah. Perfect now? Yeah. Great. Java streams and functional programming in general is something that we rely on. And hence I have chosen this topic today because this year we also have 30 years of Java. And I wanted to look at something that evolves over the time and see how exactly we are using this, how it changed from the very beginning, why it was introduced, and so on. Before I jump into the subject, I'll share that administrative slide. So for the questions section, simply access the QR code that you have seen so far a couple of times, or get to the URL directly. The code is GeeCON, and we are in room number 1. Well, with this set, let's discuss a bit about what we are going to see today. And in approximately the next 45 minutes, we are going to explore a topic that has become absolutely essential in modern Java development, and that is Java Stream API as mentioned. Whether that you are an experienced developer or you have just started working with functional programming, most likely streams have played or will play an important role in how you write or structure your code. Therefore, we are going to explore how Java streams work, why they were introduced in the first place in Java 8 a couple of years ago, and how they evolved all the way from Java 8 till Java 24, which is at this moment the last release version, but you all know that in September we will have 25, so it's plenty more to explore over there as well. And here is what we will cover today. First of all, we will start with an introduction on the streams topic itself, so what they are, how they differ from traditional iteration, and the core principles behind them. Next, we will look at the motivation behind streams, so why they were introduced in Java 8, what are the problems they were aiming to solve with them, and especially with a focus on verbosity and parallelism. Then, we will break down that stream pipeline architecture, so how the data flows through a stream pipeline and what makes the architecture for them so powerful and efficient that we are using or we have to use them. Afterwards, we'll clarify the roles of intermediate and terminal operations, which are some key concepts for building well-structured stream logic. Then, we will explore the type of streams that are available. We have 4 of them that we are going to look today with some examples for each of them, sorry. Then we will explore or more walk through the evolution version by version with a focus only on the main changes, those that were highly important. So we will highlight some of the new methods that are representing some best practices to use, some of the enhancements and performance improvements that were made with streams along the way. Afterwards, towards the end, I will share some of the best practices and common pitfalls at the same time, and I will provide you some of the examples for do and don'ts that I have also seen in practice, so I will share them with you. Finally, we will touch on how streams connect to the reactive programming through the Flow API, which is opening the doors for asynchronous or non-blocking data processing in modern application. And of course, we'll finish with a quick summary and Q&A at the end. So feel free to just type your questions in that Slido application. So let's get started. And our first topic is the introduction to Java streams, as mentioned. So let's kick off things with a high-level view of what streams are and why they exist. Well, we know so far, because I repeated a few times, that streams were introduced in Java 8. And they are part of that stream package. And I honestly believe that they changed how we process the data. At its core, a stream is an abstraction for processing sequences of elements, if we were to provide a definition. So imagine having a collection of data. It can be a set, an array, a list, and so on. And instead of manually iterating over that collection, stream let us express the operation in a very more declarative way. So in essence, streams provides or enables something called functional style operation on this collection of data. So this means that we can simply apply what we want to do. We want to filter, we want to map, we want to reduce, and so on, all in a more concise way. So we focus on what we want to do with the data and now how it gets done. Streams provide this for us. And the functional style nature comes from the fact that we treat data as being immutable. And we apply pure functions, so operations that don't modify the original data, but instead return transformed results. So with streams, we don't write loops anymore, and we don't worry about intermediate states. This is what streams offered for us. All right. Now, let's take a quick look at some of the key characteristics that actually make streams so unique and efficient, because I keep repeating that they are efficient. Let's see why. First of all, they are declarative. In other words, you express, as I mentioned a few seconds ago, you express what you want to do with the data and not how to get the data. And this is the key difference from the traditional imperative programming, where we have to manually iterate through the collection, either with a loop or a for and so on. We had to check the conditions, we have to accumulate the results, and so on. With streams, we simply declare the operations on the data that we need, and the streams handles all the internal mechanism for us. But there are more than that. Streams also employ lazy evaluation. This means that intermediate operations like the one that I have mentioned so far, like map, like filter, like sort, they are not executed immediately as we type them in the code. Instead, they are only being executed when a terminal operation like collect or for each is triggered, or they are triggered. For example, if we want to filter the elements, but we only need the first few that match, let's assume that we want the top 3 out of a collection of data, the stream will loop processing only until it meets the condition. And that's it. He will handle everything for us. Another great characteristic is the fact that streams allow chained operations. This means that we can take multiple stream operations, so at the same time we want to filter, we want to map, for example, we want to transform a collection to uppercase, then we want to apply some more logic on it, and we can do that in a single pipeline. We can chain all of those operations in a single line of code. And finally, one of the biggest benefits of streams is their potential for parallelism. So by simply calling parallel stream instead of simple stream, we can convert a sequential stream into a parallel stream, which processes elements concurrently, as the name states. And this can drastically improve the performance when working with large data sets, because we already learned in a couple of other presentations that took place this week on the stream topic that they shouldn't be used in quite all the scenarios, so we need to be careful when you use the parallel streams. They work mostly when we have large data sets. Okay. Now that we have seen some of the characteristics, the key characteristics for streams, let's take a step back and talk about why streams were introduced in Java 8 in the first place. And there were several motivations behind this shift, and I think that by understanding them will help us appreciate more the impact of streams in our development. And first of all, as you can see here, we have something called imperative limitations. So we were stuck in our development previously with the imperative style loops for processing collections, like using for and while loops. These approaches are or were verbose, error-prone, and sometimes they were difficult to maintain, especially when we have some complex logic. For example, just a simple task of filtering a list of names, for example, printing out those that start with the letter A, it required multiple lines of code. We had to manage the loop, we had to check the conditions, and we had to print the results. So something that was repetitive and maybe unreadable. Maybe not in my specific example because that is something simple, but we can get to some complex logic for this. Another reason, another motivation behind the streams part is related to the functional programming paradigm. So Java has always been an object-oriented language, but there was a growing need for a functional approach to handle collections more expressively and concisely, if I can say so. And I can say from our own experience at Systematic, at least when we are using a very old Java version in our application, because we needed more, we needed to improve our way of development, we started to use Scala, because Scala offered us the benefits of functional programming. And only in recent versions, when Java got the same level of functional programming like Scala did, we started reusing Java again in our application, and we ended up with having a mix of combination between them. But there were times in which other programming languages were offering us more benefits than Java. So we consider a huge improvement since Java 8 when functional programming was introduced, and along the versions with how it got evolved. The next reason I could mention is the parallelism, and it's actually the last one. Well, another challenge with the traditional loops was the difficulty of parallelizing operations, because multi-threading in Java requires managing threads manually. And sometimes it could get messy, and if we were to have some problems, it could have been very hard to debug. With streams, on the other hand, the parallelism aspect is built in. So we don't have to worry about thread management. We can simply switch to a parallel streams, and the framework handles everything for us. So minimal effort from our development side. If I haven't convinced you with the theory at least, let's look at some of the examples that I have here. And the first one, I will show you how it was in the old days with just the imperative style. So in this example, it's something that I mentioned previously, only that we are looking at some code now. We have a for loop to iterate over a list of names, and we check there if they start with the letter G. If they do, we print them. So simple. But notice that we are manually managing the loop and the conditions inside the block and so on. Now, let's compare this to the stream approach. So with the declarative style, where what we are doing here, we declare the list exactly the same as the imperative style, no changes here. But afterwards, we simply use the filter method to filter out the names that starts with the letter J. And then we use for each to print the results. And I honestly believe that the code is now more concise, more readable, and it's easy to follow. If we were to look in parallel of those two, I believe the one on the right side with streams, so declarative style, is much more readable. So as you can see, the imperative style loops were limited in terms of readability. And let's continue to see how they evolved over the years, because this was something that was available from the very beginning when they were introduced. And I'll start actually with how the stream pipeline is structured before we get to the evolution, because it's important to see first how the data flows through the stream API. And we have three components. Let me bring them one by one. First of all, a stream always begins with a source, which can be a collection, like we have seen in the previous example. like a list or a set, or it can be an array. So this is the place where the data comes from. Once we have the source, we apply something called intermediate operations, and we will define them shortly in a more advanced way. So at this level, we have the operations like filter, like map, like sort, which transforms the data. Which is important to mention is that these intermediate operations are lazy. So they are not executed immediately, but instead they are added to the stream pipeline for further processing. So up until the moment when we get a terminal operation being triggered. And these are the ones that actually consume the stream and produces a result. And here we have operations like collect, like for each, like reduce, and others. And once we call one of these, then the stream pipeline is being executed and the data is processed accordingly to the intermediate operations that we have defined previously. And we already seen that we can chain multiple of them. Good. And if I were to simplify the text by showing you a diagram, it will be something like this. So we have the data flowing from the source. Then we apply the intermediate operations, which I mentioned that they are lazy. They build the pipeline, but they are not triggered at that moment. And we end up with the terminal operations that actually triggers the execution and provides us the results. Good. And let's now tie all of this together with a practical code example and show you a complete stream pipeline in action. So in this snippet, I start with a list of names. This is our source that we have seen, the first part of a stream pipeline. First, we filter the names to only those that are longer than 3 characters, as I have written over there. So this is an intermediate operation, part of the second part of stream pipeline. Then we map each name to uppercase. Once again, an intermediate operation. And we also want to sort that result at some point. So another intermediate operation. So see, we have 3 intermediate operations all chained together. We can also put them in one single line if we want. The idea is that we can even make it shorter if we really need to do that. But for readability reasons, I have added them like this. And afterwards, we have finally the terminal operation where we try to collect, and at this moment, the entire pipeline is processed. And we get the result printed with the transformed data that we have received. And now that we have seen a practical example, let's define a bit those 2 keywords that I have repeatedly used so far. So to truly understand how stream pipeline works, we need to distinguish between intermediate and terminal operations. So let's look at them. The intermediate operations are the ones that build the pipeline. They include methods like the ones that I have mentioned, filter, map, sort, etc. Those are lazy, and they return a stream because they don't execute at the moment of using them. So we can say that they are composable, and we can obviously chain multiple of them. While the terminal operation, nothing happens until we call them, because they are the ones that kick off the processing. So terminal operations are the ones that consume the streams and produces either a result or a side effect, because we can also just print or transform to uppercase and so on. And among the examples we have for each, collect, count, reduce, and so on. This was the difference for those 2. And we can see both of them in the previous code that we have just seen. I just show it again to you. I mentioned at the beginning that we will look a bit of the types of streams. Because there are 4 types. I will start with the first one, which is the most commonly used, the object stream. It works with any references type, like strings, like custom objects, collections, and so on. And I have here an example as well, where I have used stream of method to create a simple stream of strings. So this is the most frequently used, the most common one. And we can use it in an example similar like this to create just a simple stream of strings where we can apply afterwards a lot of operations through those intermediate and terminal that we have seen recently. Then we will have the primitive streams. And here we have examples like int stream, long stream, double stream. So they are more optimized to work with primitive data types without the cost of boxing and unboxing compared to the ones that we have previously seen. And they are very good for numerical data processing. And I have provided an example over here. I have used the int stream with a range from 1 to 10, which simply produces numbers from 1 to 9. So this is the primitive streams in action. Afterwards, we have something called parallel streams with just one method call, which is parallel stream. We get a stream that splits its works across multiple threads. We need to be cautious, as I mentioned, because not all operations benefit from this, and thread safely is crucial in our applications. And I also have an example over here where I have used parallel stream on a list of integers. Afterwards, I just square each number and with a map operation, and afterwards I print the results. So since it's a parallel stream, the processing might happen on different threads simultaneously, which is why the output may not appear in order. But in terms of processing larger data sets, this is really useful. And this is one of the examples where parallel streams can be used. Obviously, with a larger data set, not my 5 numbers over there. And the last type of streams is represented by the infinite streams. These are streams that don't have a fixed size. So they can, in theory at least, go on forever. They are created, for example, when we use generate or iterate to produce values dynamically. And I also have an example over here. Here I have used the generate method with a met random with a limit of 5 because it is advisable not to let that stream go on forever. We need to limit to prevent memory issues. And in this example, basically, I have generated 5 random numbers by using an infinite stream. I also try to sum up all those 4 slides, one for each of the stream types, by looking at this diagram now, which gives a clear overview of them. As you can see, each stream is suited on different scenarios. The object streams can be used anywhere. They are the most commonly used ones. Then we have the primitive streams, which are optimized for numerical data. Then we have the parallel streams for efficient multi-core execution, and infinite streams that can generate continuously sequences of numbers, if we need a scenario like this. And finally, let's go a bit for the evolution of streams over time. And for this, I'd like to discuss about the beginnings first. And that's because Java 8 was, from my point of view, a game changer for the language, because by introducing the stream API, it allowed us to perform functional style operations on collections of data. For example, with a simple stream pipeline, we can process data by applying operations like filter or map. And this means that streams allowed us to move from the imperative code style that we have seen at the beginning in those 2 examples that we looked in parallel to a more declarative approach. And additionally, in Java 8, we also had parallel streams that were introduced, and they enabled us to take the advantage of multi-core processing without the complexity of handling manually those thread management processes. And I think I already walked you through the importance, but I forgot to load the text. Sorry for that. Let's move on and look a bit at what Java 9 brought to us, because it also had some improvements, very useful improvements, like take while and drop while. These are 2 methods that made the stream iteration more flexible. And I have there some examples as well. Please look at the first one with take while example. Here we can see that we can take elements from the stream as long as the condition holds true, which is great for conditional processing. So in this example, I have used take while to stop iterating as soon as we encounter an element that doesn't meet our criteria. And in this case, that criteria is that it shouldn't be greater than 10. And this is particularly useful when we work with sorted data. On the other hand, as I mentioned about the second method that was introduced, drop while does exactly the reverse thing. So it keeps the elements from the stream as long as the condition holds true. And this can be as well useful when we want to discard the elements from the beginning of the stream, for example, until a certain condition is met. And Java 9 introduced more actually than just these two methods, take while and drop while. It also introduced optional stream, which enabled us to convert an optional into a stream. And this is quite useful because it eliminates the need for us to explicitly check for a value first. And we have here the last example from the slide, the one from the bottom. We have here an optional string that holds the value Tom. And then I have used the stream method to convert this optional into a stream and then apply a filter operation. Since the string I provided passes the filter, it is printed as the output. But if the optional was empty, the stream would have been empty. So nothing would have been printed, but we didn't had to check the value first, and obviously we don't get any errors. Let's move to the next version that introduced something quite useful as well for the streams, and that is Java 11. While it didn't introduce quite major changes to the Stream API itself, it provides a few improvements that indirectly enhance the Stream usability. And one of the more notable features here, I would say that is the possibility of using var in Lambda parameters, which improves readability. And I have once again added an example here where you can see the use of the name var variable, which is further used to convert the uppercase. So starting with Java 11, var could have been used in stream scenario like this. Going forward, we have Java 16. It brought a small but highly appreciated functionality, quality of life improvement, if I could say it like that, with the introduction of the toList method, which is applied directly on the stream interface. Previously, when we wanted to convert a stream into a list, it requires us to have that collectors.toList, which was a bit verbose, not that much, but it was. While with this new method, we can simply call toList, and that's it. And it's more cleaner and, from my point of view, a bit more readable as a code. I also have an example here of how this is being used, and I think that it's also worth mentioning that the list that is being returned is unmodifiable, so which is quite ideal to ensure data immutability. Let's see what the next version is bringing to us, and I'll jump directly to Java 21 because this one introduced a powerful new method, and that is map multi. I'll also load the example here. You can think of map multi as a more controlled and efficient alternative to flat map because it is especially useful when you need to map a single element to 0, 1, or multiple outputs without creating intermediate steps or intermediate streams. In this example, I have taken each number and emitted both the number itself and its multiply of 10 using a consumer-based approach. And this is more performant because it avoids creating and merging all those multiple streams internally. So this is one of the examples where map multi can be used. And there's more. We have now stream gatherers in preview future starting with Java 22. I load the example as well. I believe you already seen a presentation on the stream gatherers these days, so I won't spend too much on it. I just want to mention that this allows us to use the new gather method to collect the elements into the stream into a more flexible structure. And in this example here in the provided code, we take a list of strings, we break it into groups of size 3 in my example, using the gatherers window fixed with an argument value of 3. And this change simplifies our code when we need to work with data in batches, because we don't need to implement complex logic ourselves. So this is quite handy. Let's move to Java 23. We also have several enhancements being added in this version, starting with the transform method. I could say that this new method enables a functional transformation of streams elements, also in a more concise, readable way. And in the example that I have provided on this slide, I have used the transform method to convert string to uppercase. And this, I think, it demonstrates how this method allows us to easily apply a function to each of the elements in the stream. And in the addition to the stream, to the transform method, also the parallel stream processing has received important improvements in Java 23. And those improvements are mostly related to how the JVM can now more efficiently distribute the work across multiple threads. So this is something internal, but it's an improvement in terms of performance. And lastly, in Java 24, I'll load in a second. This also introduced a couple of key enhancements to the Stream API, and they are mostly important for data manipulation, but also for performance improvements. And one of the most important changes, as you can see here, is the introduction of flat map to int, flat map to double. These two methods allows us to flatten a stream of collections into primitive types like int and double. And they are useful when we work with large sets of primitive data types, for example. And in the example that I have provided over here, we are flattening a list of lists into a single stream of integers. So this is more memory efficient than simply using a stream of integer, because it operates directly on the primitive int type. And I think that Java 24 is a great choice for high-performance applications, but I'm also looking forward to see the changes in 25 in terms of working with streams. But in terms of evolution, this is where I stop with version 24. And because we have seen quite a lot of changes, I would want to take a break from them and look at some of the common best practices and pitfalls at the same time while we were working with streams. And I'll also provide some code examples for them afterwards. So, first one on the list. You use streams for simple and composable operations. What does this mean? It means that the streams are great for tasks like filtering, like mapping, like sorting, because they help us avoid complex logic within a stream pipeline. Another best practice is to take advantage of lazy evaluation. This means that because streams are lazy evaluated, they are processed only when terminal operations are being executed, and this helps us avoid unnecessary computations. Another best practice is to take care of when you use for each, because it's useful for consuming elements, and it is often better to use other terminal operations like collect for aggregation, because for each is in a parallel stream, for example, might lead to non-deterministic results. And we will see shortly an example for this. It is also recommended to prefer parallel streams just for large data sets, not with 1, 2, 3, 5 numbers like I have in my examples. They provide automatic parallelization, so we do need to ensure the tasks that we are using are independent and the dataset is large enough to justify those parallelism operations. And lastly, in terms of best practices, I would say that we should avoid modifying shared state. When we use streams, we need to avoid modifying external state within the pipeline, like a list, like a counter, because this may lead to unpredictable results, and it is hard to debug if we have a problem. And among some of the most common pitfalls this time, I will also list a couple. First of all, we should stop overusing parallel streams. As an analogy to what I've just mentioned, to be careful while using them. They should not be used when they are not needed, if I can say it like that, because they can introduce overhead and degrade the performance for small tasks, as opposite to what we are expecting them to do, to improve the performance. We also need to be careful about the side effects. So streams should ideally be side effect free, because modifying external variables in a stream operation can lead to hard to trace bugs. If we have a problem and it was about how we have written our code with streams, it can be very hard to debug it sometimes. We had this one a couple of times in our development environment as well. Afterwards, I would say that it is recommended to use for each instead of other collectors, because data can be proper accumulated with collect, for example. Afterwards, we need to be careful about the type of operations that we are using. So we should not confuse the intermediate and terminal operations. The first one are lazy, are not executed until the terminal operation is invoked. We've seen this a few times already. And confusing the two can obviously lead to unexpected results and potentially performance problems. And let's take some code examples over here. And I will load them. All right, so I showed you previously that example with having a list of streams, filtering after those that the names start with G. So let's start with this. So on the left side, with the best practice, it means that we should avoid side effects. So using collect in this example is clean and safe. But on the other side, if we look at the right side example, modifying an external list inside that for each breaks the functional approach, because this is especially problematic when we work with parallel streams, but as I highlighted there, it can lead to side effects. So use the approach from the right side, and don't modify external list in a for each. Second example, I will load it now. It's about parallel streams, which I mentioned we should use quite wisely. In the first version, in the first example, I'm using filter followed by count, which is concise, is functional, and thread safe. So no problems over here. Each operation is stateless and doesn't interfere with the others, exactly how streams are meant to be. Let me load you the second example. And here I have introduced an atomic integer, and I have mutated it inside the for each operation. So while it technically works, it breaks the declarative and functional style that streams are designed to promote. So it relies on side effects, especially mutating external state during the stream execution. And in a parallel stream context, this is quite dangerous, because multiple threads can be updating that same atomic integer at the same time. And even if it's thread safe, because it is by definition, it introduces some synchronization overhead and potentially confusing behavior. And let's look at the third example. I love the first one with the best practice. Let's take a closer look at this comparison between using all match and manually simulating the same check with for each and the flag. I load the second example. So the goal here in this example is simple. We want to know all the names that have a length of at least 3 characters. The version with all match, the one from the best practice, is clean and is self-explanatory. It expresses the intent directly. We are checking a condition across the entire stream, and the result is returned immediately after the condition fails. That's lazy evaluation in action. And it's efficient. On the other hand, the second version, here we take an imperative route because we declare an atomic boolean, we iterate with for each, and we manually mutate that flag that I have used over there, that valid variable. This introduces a shared mutable state which increases the risk of bugs, especially if we switch this example and transform it into a parallel stream, for example. And there's another subtle cost over here, the readability. So in the second version, we are forcing the reader of our code to follow the flow. What we try to do there, we had a valid parameter, we mutated, we set it to true, to false, and so on. While the other version is a bit more cleaner. And as a wrap up, so as a summary of what to use or not, I would say that it is highly recommended to use collect for gather results, to change stream operations, like we have seen in a couple of examples so far, to use status lambdas with it parallel stream, and to prefer expressive terminal operations like all match, any match count, and so on. On the other side, what not to use, I would say don't modify external variables inside the stream operation, and we have just seen an example. For each used for logic instead of side effects, and use shared mutable state in parallel streams. This shouldn't be used. All right, I think we still have time. Yes, we are good here. So let's take everything that we have learned so far and apply it to a realistic business case scenario. It's something simple, but it can be extended to something that we are using in our practices. So let's suppose that we have a list of users and we want to extract some meaningful insights over there, like how many adults, persons, you have per country, something simple like this. In the traditional imperative Java, we would probably use nested loops with some conditionals, which would be verbose and harder to maintain. So let's see the stream approach. Here, stream let us express the logic in a clean and declarative way, instead of having those loops with conditionals and so on. So let's look at what I have written here. First of all, we start with filter to keep only users who are active and over 18. These were the conditions that I have mentioned at the beginning. Then we are using collectors grouping by method to group users by country. This was also one of the requirements. And finally, we apply collectors counting to count how many users are in each group. Once again, one of our requirements. And the result is a map, string long, which maps each country to its count of active adult users. So those users over 18 years old. The restrictions, the conditions that we have specified at the beginning. And since the pipeline is composed of pure operations with no side effects, as we have learned not to be careful about, this approach is naturally safe for parallel stream execution too, if we were to have quite a large data sets over here. And I believe that you'll see patterns like this quite often in real systems, whether you're processing users, orders, logs, sensor data, military users information like we have in our application, it's systematic, and so on. And I think I have time just for touching up on a topic that often comes in modern Java application, and that is reactive programming. I won't insist too much on this because it's the topic for another presentation, but at least I wanted to give you something to explore further into it. If you've heard of libraries like RxJava or Project Reactor, then you're probably already familiar with the concept. What I want to mention is that in Java 9, we have seen what it changed for Java Streams API itself, but at the same time, Java 9 introduces Flow API, and it was introduced to support reactive streams, so a standard for non-blocking asynchronous processing. Now, while Java Stream and Flow API difference is clear, I have also shown here some diagrams on how they can be integrated. So the Flow API supports back pressure, if I can use this term, which prevents overwhelming the consumer, while the Streams API, initiated by the developer, on the other side we have the Flow API, which allows the data source to control the pace. So if we are building a responsive or a streaming application, for example, like data ingestion or some UI events or microservices, then it's worth exploring how Streams and Flows API can coexist in your architecture. And I think time's up. So thank you everyone for attending, and let me switch to questions to see if we have any. And yes, we do, but I also need to show them to you, so let me... All right. We can both see them. All right. Let me see them on my phone as well, as I have shown them to you, but not for me. So, the first question for the top, let me see if I see it correctly. How is transform different from map? It's a little bit more efficient in terms of the internal mechanism, but in terms of what it does, it's pretty much the same. So I did hope I answered this question. The next one, how is, let me move it a bit. So, how is box necessary after map to int? Doesn't it negate the performance benefits of using int stream? I would agree. I agree, yes. But still map to int is more efficient during the processing part. So once we process what we need on those primitive data types, we have the performance over there, but yes, at the end we still have the boxing concept. So you may argue that in terms of performance, it decreases with the benefits of using int stream. How does take while behaves on unsorted data? Stops at first value, which breaks condition, or check all other values till the end? No, it stops at the first one that breaks condition. So you need to be careful on using it on sorted data. Otherwise, the results can be unpredictable. So, should you stop using map and start using transform for every case? No. You should first explore both of them and see if on the data you're using them, the performance is better. There are cases in which map is still efficient, there are cases in which transform is more efficient. Why do you judge which cases are too complicated to use streams and which aren't? Oh, how do you judge? I believe this is a bit subjective. So if I see a method that is 50 lines of code, okay, I exaggerate now. If I see a method with 10 lines of code that would have been written in like 1, 2, 3 rows with streams, then I will definitely use streams over it. If the logic from my for loop, for my while iteration over there is also complicated to follow, I have a lot of flags, etc. in that logic, then I would rather prefer using streams. I don't see a use case for setting an external variable as optional and then applying stream on it. It's for manipulation inside another stream chain, right? Yes, yes, you're right. I just provided that example because it was something that was introduced in the API. So it was just a matter of listing what it appeared. Can we use business logic inside the stream or just data transformation? I personally seen cases just with data transformation, not with business logic inside. So I will suggest to use it for just data transformation. How to handle exceptions efficiently in streams? That's a very good question. I would like to know exactly what kind of scenarios you're referring to. It pretty much depends on the exceptions, but I think that we don't get that much with streams. It's more a matter of making sure not to mutate states inside the streams, not necessary to handle, because the mechanism of streams handles most of the internal for us. And I think the last question, is peak method always safe to use, or is this something ignored? Sometimes. Sorry? I think sometimes it's safe. I'm not sure. I would say it is safe. All right, and I think that was it. Thank you everyone for attending, and enjoy the rest of the day.